Everyone, thanks for joining today. We have a special guest whose research as Munich NLP community we closely follow on Twitter, on his social media. The research he does is really practical in nature. That's why we were very excited and looking forward to this meeting. So without further ado, I would set the stage to you. Thank you very much.
Thank you. Jump straight into it.
Sure.
So, not many can pre-train. If you've seen Mosaic, then maybe everyone can train now birds, but whatever we call large language models is always large enough to be out of reach. But I would say that anyone can fine-tune or adapt. And I assume that probably everyone in this meeting, or almost everyone, have adapted a large language model in some way. Fine-tuning, efficient fine-tuning, adapters, and many other ways.
What is fine-tuning?
What is fine-tuning? Basically, if we ask about what is fine-tuning, then let's take a step backward and say what is pre-training. So the oldest paradigm was, if I have a task, I just take a lot of examples and I train a network from scratch by seeing a lot of examples, positives, negatives, and telling the network to do the same. Pre-training says if we can get enough data and put a lot of computing effort into learning this data, then we can learn on a lot of unrelated data something and then reuse it for our own tasks. Fine-tuning would be to take this large language model, if we pre-trained on language tasks, and adapt it, train it to our own task or something like that. So if we have sentiment analysis as our target task, fine-tuning would be taking a model and training it to do sentiment analysis.
Okay, thank you.
Okay, so we were at pre-training is something that is probably out of reach, but fine-tuning is something that in some sort of way many of us do. And the main vision and question that would that I would tackle from different aspects today would be: could we reuse and recycle those different adaptations in order to pre-train models together? In order to pre-train models together, could we in some way take the sentiment analysis and the legal text classification and the syntactic classification and a lot of different things that many of us do, could we somehow benefit from each other and get better results by sharing? So that would be the overall vision of the general things I'm gonna talk about today. And before getting a bit more into details, I'll just say that feel free to interrupt. Some of you already used the freedom, so it's great. I'm here for you, and I want it to be interesting. There's no reason for me to talk about things just for me, right? So feel free to. Before getting into the details of what I'm going to discuss today, basically there are 4 layers that, or 4 papers they're going to. So there are about 4 layers of about 4 papers we can discuss, and they could be thought about as in layers. So we, in short, said what is pre-training and fine-tuning, and that would be we do some very large computation to make a good initialization model, and then we adapt it to our target task, and different people do it for their own task. Then instead of using this large model that someone trained once, we can take something that someone else adapted, right? We said that already different people adapted their own models. The third option might be, instead of taking models that different people fine-tuned, could we take two models that someone else fine-tuned and somehow fuse them to make one model out of them and start from that? That would be the third option, and the best outcome, the last goal that we would also end with, is could we do it again and again and again? Could we, instead of taking a pretrained model, and instead of taking one fine-tuned model or several fine-tuned models, could we take a pretrained model, let people use it, and when they share enough model, fuse it into one, and this one would be better, so people would fine-tune on it, they would use it, they would make a better one, and then we go back into an evolving paradigm like we have in code and like we have in Wikipedia, where people edit and improve and so on. So that would be the vision. And just one thing before we get to the details is why do we even talk about pre-training? Basically, we use pre-training because we have some architecture that we care about, and we could have randomly initialized it. We could have just chosen any weight in all of the space, any point to start the model from and train on it. But we found out that pre-training makes a better initialization for any of our tasks better. And it's already known that this is not the optimal point. We know that sometimes there are better points, and obviously, if we already could have initialized from our model after fine-tuning, that would be the best point, but we don't know that. There are questions in the chat. No, it's just that to use it. Okay.
I will read it out and stop
Okay.
you. Yeah,
Thanks.
no problem.
Okay, so I think the setting should be more or less clear, but let's make it one last time clear to everyone. What we talk about now is the case where you have a pre-trained model and you ask whether you should use the pre-trained model or one of the multiple models that were fine-tuned somewhere and shared. For example, in Hugging Face, there's more than 1,000 variations on Roberta base. Could we just use one of them instead of us when we come with our own target task that we care about? Okay, so a lot of introductions, and now we can get to learning some new things, experimenting and so on. So the first experiment would be something like that. Consider the case where we take a lot of models. We just go to Hugging Face and download 66 Roberta based models. Then each one of them we test on different data sets. We fine-tune each one of those models and test whether it is good or bad on this data set. And specifically what we really care about, and this would be the color scheme, whether it's better or worse than Roberta pre-trained, whether taking this model is better than taking the pre-trained model that someone already shared. And we did it many, many, many times. And this is what we see. Okay, so the first thing that I would assume you also see in the table is that it's mostly purple and not green. So in a very general notion, it's not a smart thing to just go out there, download the model from Hugging Face and use that instead of Roberta. But we do see that there is some consistency. For example, we see that there is some tendency along the columns. So we can see that some columns are about white, so the initialization don't matter to them much. And some columns, which means some data sets, really care about choosing the right initialization. So given your task might really care about starting from a better point than starting from just the pre-trained model that was randomly assigned to you. That is nice, but in a sense, we just have our data set or our target task, and we can't change that easily. What we can change is the model, so the rows. And we see that although most of the table is purple, some of the rows in the table are not only green for some data sets, but they are always green or almost always green, which tells us that sometimes there are models that are just better for more or less any task that we take. And that would be what we expect from a good pre-trained model, right? Why would you choose, why are large language models so popular? Because they are better than smaller large language models. So Roberta large is just better than Roberta base on most of the tasks you check. So people do not need to think whether Roberta large is good for their task, except for efficiency, which is a legitimate thing to consider, but separate thing. So here the important bottom line is that there are models which are just good models. They are better than the pre-trained model, and they are better consistently. So there's no reason not to just pick them and start from them. That's it for them. But we don't really know why are those models, so which models are going to be those good models. One hypothesis that people might think is that those models are good because they kind of have weak label data. What does that mean? It means if I have MNLI, some natural language inference task, maybe it would benefit from SNLI because it's also something about natural language inference. And then I kind of trained the same thing twice. I took a model that someone else trained on natural language inference, and I started from it to train my own natural language inference. Then I could expect that the double training would somehow help me. So in order to check whether this is the case, we did the same experiment as before, but now we did it with our own fine-tuned models. So now each row is a different model, but we know how it was created. It was created on a different data set. And we have squares that tell us whether the different data sets are of the same task or are related. So in the diagonal, we have models that are trained and tested on similar tasks. And on the non-diagonal squares, we have models that were trained on one data set and tested on a different data set that is unrelated to them. And what we see, and we can also check it with significance testing and regression and those kind of stuff, is that it's not really the weak label data effect. Instead, what we see is that if you don't know which model to pick from the hub, it's better to just pick a model that is close to your model. It gives you some effect. But it would be much better if you just took a model that is in general good. So if you would have known to rank the models by better than each other, then a model that was good on different data sets would also probably be good on your data set.
May I ask one question?
Yeah, I wanted to.
Yeah. So just in this line, how do you capture this notion of similarity here?
So
like,
here,
is it like cosine similarity, embedding similarity, or TF-IDF?
So here we made a very simplistic similarity and just said, okay, all of them, the data sets that are on really the same task, they're all similar. SNLI, MNLI, ESNLI, RTE, those kind of tasks,
Okay.
or Twitter sentiment analysis, Twitter text classification, Twitter. So all of those are in the same domain, not task, those kind of things. So very broad, and in that sense, you can assume that it's even more helpful than something that is only on the, like, it has a cosine similarity, but it's not really the same task. This is really, really the same task, and it's still not helping that much to each other.
And what are your hypotheses for why it's not working? Of course, there are many factors, like even
so
kind of initialization of neural networks. I don't know, but what are your hypotheses here?
So in some sense, it is working better than picking at random. So there is some effect. It's better to pick. It's better to pick something that someone else fine-tuned on a data set that is like yours. But it is just much better to pick a good model. And the assumption is that some good models learn something important, and that is more valuable than the memorization or understanding your task or something like that. Because that you would get from your own data. But just like that, pre-training is unlike random initialization. It has some inherent, you can call it, sometimes people call it emerging capabilities. So it has some capabilities that are now in it, and those are general things that could be used in most or all different tasks. So it's useful to start from them.
Okay, gotcha. Thank you.
So that's the assumption.
Thank you. I guess we don't have any other questions from chat, so I muted everyone because there seems to be some trolls, but I will read out. Sorry for,
Yeah, probably that's also raising hands and stuff.
Yeah.
Okay, so the bottom line was that if we rank models and we can tell which model is better than which, then we can just use this information and start from the good models, because it doesn't really matter which task do we care about. Whatever the task is, mostly the same models are the same good models. So the only thing that is left to do is to go on all of the models and try them. But that is a bit costly. You wouldn't want for your one task that you just wanted to do on the side to go out there and fine-tune the 1,000 Robertas. So one thing is that we found a way to approximate it and do it more efficiently. But even less costly is let someone else do it. And understanding that, we thought that we are the only one that should be this someone else. So we do it for you. What we suggest is just that we have a site, it's already online and running, and we periodically go out there and download models from Hugging Face and just share how well did those models do when we fine-tune them. So for each architecture, we test many models and share both the average and the score per task. So if someone really cares about something specific, they could check that. And also we share all of the data. So if someone suspects that they have an idea of why would some models be good for some tasks and not another or anything of this sort, it's all out there. There are also several architectures, and if anyone is interested in something that is not there, then just reach out and maybe we'll just add another one. That's it. It's up and running, and you welcome to use it. Questions before I go to the next stage? Okay. So we found out that we could just pick one model, let's say from Hugging Face, and use that, and it would be better than starting from the pretrained model. The next question would be, could we pick two models instead of one? Could we somehow fuse two models and get one model that is better initialization for our task? And this might sound similar to you from other papers that you know, because we've been in parallel, 3 people wrote about something similar like that with different goals. So our goal is to take several models and fuse them into one that is useful as the pretrained model. You might know model soups that care about models that run on the same data set instead of different data sets, or Colin Raffles and Michael Matenas that care about improving the results of an already tuned model. So how do we do it? How do we take one model, two models, and make them into one? Obviously, it's something that is nonlinear, and we couldn't just fuse them out of the air, right? We couldn't average the weights and expect for something to work. So we even do. And just to emphasize the difference here, we don't do ensembling. We don't average the outputs of two networks and do something like a majority voting, telling, okay, this says this probability and this is another. We average all of the weights of all of the networks together. And then we get something that has no mathematical guarantees that it would even get an output that is anywhere similar to any of the two, because it's a non-linear function, so the parameters are not a linear function of the outputs. So averaging doesn't have to mean anything. Okay, links. If any links, anyone care about links in hindsight, or is missing papers that I referred to, links, the website, you can always send me an email or Twitter or whatever is easy for you to contact me, and I'm happy to share it. Okay, so this very naive and supposedly shouldn't work. I mean, I had some reasons to try it to begin with, but non-intuitive at least. We just do that. So now, instead of going to, let's say, Hugging Face, taking a lot of models and testing them as is, we take pairs of models, fuse them, and test whether they are better than the pretrained model. And this is what it looks like, a lot of numbers, so bear with me for a second. We have here on the diagonal axis, we have the models fine-tuned like before. So those are models that were fine-tuned on COLA, SST, MRPC, and so on. And each one of them was tested by fine-tuning again on 36 different data sets. And the number here is whether the average is higher or lower, and by how many points than the pretrained model. So -2 means that on average, it's 2 points accuracy less than just using the pretrained model. Do not pick COLA and use it as your pretrained model. Okay, that's nice, and we see that some of them help and some do not. We've already been in that. What's really interesting here is all of the rest of the table. Now, instead of taking one of those models, we fuse two of them. This is also why the table is symmetric. How do we read it? If it's green or yellow, then fusing two models was better than just picking at random one fine-tuned models of the two. If it's black or red, then you are better off taking just one of the fine-tuned models. And in general, I think you would agree that picking a model, the average of two models is better than picking just one of the models. Okay. The next step here would be if we fuse two models and it's better than one, then why not three? There's 1,000 in Hugging Face. Could we keep on improving this way? Somehow taking some of the knowledge of this and another, and slowly getting more and more knowledge into a model until it would be like a training stage. So sadly, we can't. Here, what we're doing is taking the best fine-tuned model from before and fusing either one or two models to it. And we see that here the fusing two models is better than fusing three models. So we do not get further improvements by adding three models. Note that this does not mean that we are not better than the pre-trained. There's a lot of negatives, I'll say it again. The pre-trained model is worse than every three models that we fuse together. So take any three models, fuse them together, you got a very good pre-trained model. It's better than the pre-trained. But it's not better than taking two models and fusing those together. So we have a recipe of improving the pre-trained model, but we can't do it forever. We can just have a one-step effect, and we need to stop there. And of course, I would prefer not to stop there, and this is why the last paper would touch something that would go a step forward. But before I go to that, most people, when I would tell them about taking two models and fusing them somehow together and getting one model that even works, not to talk about being much better than the model before, would usually look at me like that. And they have a good reason to. So as I said, there are several intuitions on what could be the reasons to it, but today I would discuss one point of view of what could be related, or how could this be explained. And I will do it through the vast weighting space. So as before, we said that a random model is just a random point in this 700 million parameter space. To have 700 million dimensions, and every point in it is a valid model. It might be a very bad initialization point for our neural network of very sophisticated function, but it's just a point in the space, and because of that, the architecture could get it. It's just numbers into the weights. But what we do know is that there are points which are special, like the pretrained model and everything around it, and the fine-tuned models. There are various points that act in different ways than just random points in this space. So how does this space look like in general? It's very hard to wrap our minds around this multidimensional space, but with a very, very simplistic scheme, I would say that it looks something like that. And that would be the next paper that I'm gonna discuss. Of course, if you have questions, feel free to stop me at any time. So the idea is something like that. We have the pretrained model, and it's just a point somewhere in this space, a point that we know somehow incorporates some knowledge. And when we fine-tune this pretrained model, we reach various points. They are in various places, and in this scheme, those are the little circles around the scheme. Okay, fine-tuning reached points. It has to reach some point. The interesting thing that that we're going to discuss is that what we find is that they are not just spread around. When you fine-tune, then apparently the fine-tuned models are not just a sphere around the pretrained model. They're all falling in some general region that is a very small subset of the 700 million the directions they could go around the pretrained model. Even more interesting than that, I would say, is that when you train on a task, so we train on different data sets that have some similarities between them, then the models also fall in similar regions in this space. So we trained on different data sets, which might sometimes, let's say, come from different domain, but they share something, they share the task, and we find that they fall near each other. And you can also separate seeds. So if I fine-tune several seeds on the same data set, they would be closer to each other than several models that fell in a different, that were trained on a different data sets, even if it's a different data set on the same task. More or less clear? Questions until now?
Yeah, seems clear. I don't see any questions in the chat.
Okay.
Yeah.
In that sense, I'm giving you this too simplistic story, which obviously someone after me would come and say, no, you missed some detail, and it's not exactly like that. And surely it's too simple to be true. But let's still give some substance to this intuition and show that it seems that in some way it is true. So the easiest thing would be to look at data sets. Just here, we have 20 seeds. We fine-tune the same model on 20 times on each data set. And we try to tell with the weights only on which data set we trained on. So we have a clustering algorithm. It's unsupervised. It doesn't get anything except the distance in the Euclidean, angle in the Euclidean space, basically the cosine similarity of different data sets. And what we find is that except for the points where you see that the same point is colored in two colors, which are, for example, the green-blue ones that are down there, except those, then the cluster found the same, clustered all of the models of the same data set in the same cluster. I think at least in the data set, it's very convincing that it's easy without knowing anything about what was the training, that it's very easy to tell which data set you trained on by just giving weights. And in that sense, it means that the different weights are close to each other, or they're closer to each other than all of the other models that trained on different data sets. But saying that it's all the same data set ends up in the same space is nice, but it's not that surprising. The really surprising thing is that when you take different, when you train models that train on different on different data sets of the same task. So we take 3 types of data sets and we cluster only for 3 clusters. And we find that also now it's a bit less intuitive in the 2-dimensional reduction by TSNE, but you can still see in the colors that that the clustering is doing quite well. There are 2 data sets that it misses, and all of the rest of the data sets, it puts all of the seeds accurately to the right task. So it takes different models by just the weights and the cosine similarity, and it could tell us that models that are close to each other were also trained on similar tasks, similar in a very general way. Both of them are, for example, sentiment analysis, but they could be sentiment analysis on movies or on reviews to some commercial site. But still, sentiment analysis are all somehow reaching similar places in space and in a sense might learn similar underlying capabilities. Of course, the capabilities part is the intuition. So we find that the models are somehow close to each other in this huge multidimensional weight space. Okay, but is it just the placing of weights in weight space? Why do we care about that? What we really care about is, let's say, performance, or how good are the models on different tasks. But if we stop for a moment and think about it again, we can remember that those models are not just weights in the space that were picked randomly. They were picked by gradient descent, right? We went with gradient descent and looked for points, and apparently the points that have low loss, that have good performance in a sense, tend to be all in a similar region. So we found that there are different points close to each other that are at least approximately minima on different data sets, and that the minima on different data sets of the same task are close to each other. And even all the minima of all fine-tuned models are also close, not as close, to each other, and are not just randomly placed anywhere around the pretrained model. So there are places with special learning and special skills, the areas that have special skills. Well, at least there are points in those areas. And if you're critical, you might say, but you didn't show me anything in between those, right? We just showed that the models that we do find are close to each other. But it could be that those are minima, and between them, everything is of a very bad loss, and those are bad models between them. And now we're getting back to the point where we started from, and say, wait, we did show we have seen one point, right? We've seen the point between 2 models. The exact point between 2 models is the weight average of 2 of them. So when we fuse 2 models together, we actually reach somewhere in the middle of this region. And to prove this point forward, what we do is go on different slices of the regions, slices of the domain region, of the dataset region, of a general region, and check whether the loss of things from that region, so for example, on the NLI region, are the average loss of different NLI tasks, not one specific, are all of them together good in all of this region. And we find that this is indeed the case. So let's look, for example, on the domain region, the left graph. on the site, we find it's all average over 5 runs. We find the average score of fine-tuning on one data set and finding on another, and we can see that also MNLI is a bit better. Okay. The interesting thing here is that all of the region between those two models, all of it is better on different NLI datasets than the size. So all of this region is good and even better than the models that we started from. And in that sense, the average is just a point in the middle, in between them. And it's not even the optimal point. We can see that there is a 1.4, and on other places it could be 0.7 or something else. Okay, I hope it makes sense. Okay, and if that makes sense, then basically what we showed is that there are slices in between points that perform better on many different tasks than just the models that we can find and fine-tune them. And again, all of those models in the slice are models that were never reached by fine-tuning, and probably no fine-tuning would ever reach them. Maybe some specific data set that we don't even know the data of. But we didn't finish our claim of regions, right? We did slices. What about various points in this vast region that are not exactly between two models? We have a 30 data set. The points could be in various places. So here it's a bit less visual, but in general we see a similar trend, and I will guide you slowly to understand the graphs. Obviously, it's easier with the terms from the paper. So here again we have 3 graphs, one for each region, and we have in blue the baselines, models that were fine-tuned not on the domain dataset or not fine-tuned at all. And in comparison, we have the orange ones. And we see that in general, the fine-tuned models, the orange ones, on the relevant tasks are better than models fine-tuned on something else. For example, if we take a fine-tuned model on MNLI and test it on various NLI datasets, it's better than taking a sentiment analysis one and testing it on various NLI datasets. Again, this is related to the similarity between models and performance. The more interesting here would be that the green bars, the models between the fine-tuned models, are on the most left. So those have the lowest loss, which means that if we just pick models in random between, let's say, the NLI fine-tuned models, we would find models that are better than the fine-tuned models in general for NLI datasets. So let's give just this bottom line again. We can, if we know this region, the point inside this region, the points that are in the region of this task appear to be better than the points in the edges of the task, in the NLI task region are better than the fine-tuned on NLI different datasets. Again, a good place to stop and ask questions if you happen to have any.
Maybe I'm not too familiar with each of these data sets, but for example, is it harder to combine, or in the sense of, does the results get better when the tasks from which you combine the two models are further apart? Like, it depends, of course, on how you measure further apart, but when the tasks are very different in a human sense, does it have any effect on the models or the predictive results?
It's a good question. I would say that at least on those papers, we didn't manage to characterize at any way which combinations of models are best. Sometimes it seems that if you take at least one of the models to be just a better model in general, that sometimes you gain from it, but it wasn't something too consistent.
Mm-hmm.
And I would say that it's a good question to search. We don't have the results, and I know only one person that does something similar. They're not doing exactly that, but if they have good result, it might hint on the answer, but it's still a work in progress there. So I wouldn't even be able to.
Okay, no, of course. Thanks.
We have one more question in chat. It says, does this imply the best starting point for fine-tuning should be sampled, in parentheses, normal distribution from the centroid of convex hull of existing fine-tuned models, like including all tasks and data, in new random initialization within that region?
Yes and no. So in a sense, what we do find is that indeed, let's go to back one slide. Indeed, going somewhere in the region, and especially if you already know the region, would get you better than the models that you have. So for example, what we can do is, as you say, sample a point, take several models from Hugging Face or from wherever we have them. Maybe we just fine-tune several and take some point in between. And it should be better than the models that we started from. But it's not saying that this is what we should do, is kind of one-step solution. And why is that only one step? Because we don't know which point in all of this region is better than which. It is true that it seems that a lot of this region is better than the edges and the outside of the region, but we don't know to characterize where in this region we should fall. We can even think about this. Ideally, we would like to know where this point is for our task, or this point. But this might not be that easy, especially here is a line between two. But when we have 1,000 models or even 20 models, how would we find that? So as a small step, we probably should just start somewhere, and it doesn't have to be random. It could be any pick a point any way you want in this region. For example, some very naive approach that someone that talked to you just today did was taking the centroid, right? Taking the average of several models is just some point in between, which we don't know if it's worse or better than other points, but it's a point. A better thing would be to somehow optimize in this region, and this, to some extent, the next work tries to do something like that, and in some extent, it's an open question. The other questions in the it's the link. Okay. Okay, more questions before we reach the last paper?
I think there is no.
Okay. So, running that back, the last paper goes back to the recycling or iterative improvement of the models. And we go back to this point. So we saw that we can take two or several models, we fine-tune them, and we reach somewhere in this region, and we get a point that is better than the pretrained model. But how could we get better than that? Because we saw that we don't know where the best point in the region, and this is not the average of a lot of models. We don't get a lot of benefits from that. So the idea here is to keep on doing it. If SGD knows to find a minimum, then maybe we can find a minimum of that and that and that, fuse them, reach a point, and then do it again and reach a point, and so on. That would be the maybe theoretical side, like we did before. The maybe more exciting side would be that we can think about it as collaborating together to continually pre-train our model. So we can think about a multitask setting where each time different people come with their own data set and they take the best current model, they fine-tune on it several times, we fuse whatever they had, and now there's a new, better pre-trained model. So people go there, they download it, and fuse and share, and because they shared, we can now fuse it. So there's a new fine-tuned model that is the best pre-trained model. People keep on using that, and we have iterations. And we did just that, and it worked. It actually even worked better than we expected. So let's go start with the bottom line. The top right graph in blue is the average results on 36 data sets after each iteration. There are 5 random seeds, so you can see the shade there. And the gray scale, the dashed line, is the pre-trained model. So we see that we get quite a nice improvement over it by this multitask learning without ever sharing the data, or however you call it. We called it collaborative descent fusion, cold fusion. Two other interesting baselines would be the green line, which is the multitask learned model. So here, what we did was instead of training separately and distributively, so communication and so on, we just gave all of the data to several GPUs and let them batch and mix and so on. And apparently we got worse results than doing it on separately. We assumed it's going to be an upper bound, but apparently it's not even an upper bound. Maybe even cooler would be that the state-of-the-art Muppet is, or at least was state-of-the-art, was trained on more data sets and was much better optimized and cared for hyperparameters and things like that, because multitask learning was a known thing. And we even got better results than that. So it got really, really good results, much better than we ever expected. We can also see at the bottom left that if we don't fine-tune each time, but only have a different classification, we do something that is as close as we can to zero shot, we can see that the model actually slowly gets the information from all of the data sets that were seen during the training. And we can also see that on data sets that were never used in those iterations, that were not seen during the iterations, here it's on the few shot setting, we also have nice results. Because it was a bit better than we expected, so someone adversarial like me would say something must be off. We have to make sure that we're not cheating in some way that we don't understand. So I really try to look at the empty half of the glass, but it apparently is not that easy. So we found that I could have asked whether it doesn't generalize. And let's not bear all of this graph. There's a lot of details here for the paper, but only the top 2 lines, those 2 lines, those should be the results on the same data sets, once where they were seen in training and once where they were not. We just use the cross-validation here. So we see that seeing the data sets in training doesn't help almost at all. Maybe if you really believe this small gap at the end, maybe it even hurts the results, seeing the same data set in training. Which is very weird, right? You expect that, usually what you expect is that the test or the unseen data sets or something like that is improving, and it's not improving as much as the training because there's some overfit or something, but it at least improves. And here we see an opposite result where there's no hurt for the unseen data set. So we were suspicious, but if you think about it one more step, then actually it doesn't have to surprise us that much. Because what we see here is that our unseen data sets are not tested with 0 shots. What we test here is on fine-tuning. So basically what we're doing here is we end by giving the model data and training on it. And now we ask, if you were trained twice, once during those iterations, and then trained on your data and tested, is it better than training on different data sets and then seeing your data and being tested on it? So what we find is that seeing the same data twice is not helpful for the model, which is not that surprising. It's not that we gave it more data. Maybe it even got one more data set that is not their own. And it seems that the improvements that the model gets is from seeing different data sets during the collaborative pre-training. And the skills that it got there help it improve. And the improvement do not come from seeing their own data set twice. We could have thought that the data is somehow specific, but it seems that the improvements are nicely spread around different data sets. It's true that some data sets do not benefit as much, and even a small set of them has a small hurt to them. Maybe interesting to know at some point why and if it's consistent, but at least in general, it seems that it repeats. We also see that when we feed the same model with more and more data, then the data helps. So here we do see some positive, we have some positive feedback that it might scale, unlike having more and more models in parallel. And maybe the only thing where we would say that is not as good is that, well, if we have more contributors contributing the same amount of data, do not break anything, and we still converge to more or less the same point. If we take the same data and split it to more contributors, we need more time to converge. So when we incorporate in smaller chunks, then we need more, we waste some of our computation or data because of those chunks. time for questions about collaboratively pre-training, if you have them.
Maybe another idea here, but
Yeah.
if we can say that, for example, when we have 5 contributors, can this maybe be seen as taking 5 times the same model in an ensemble sense, and for example, making it more reliable or robust against outliers or something like that? Can there be any distinction here drawn that maybe more contributors help being more robust or something like that? I don't know if you have done any experiments in that sense, but it's just a topic that I'm currently a bit working with.
Yeah. So so here we have different data sets, which make it all a bit hard to. It's an uncontrolled experiment because all of the data sets keep on changing there, so it's a bit hard to say. But I would say that the intuitions of several people in the field is that there is some generalization benefit from somehow ignoring the overfits or the memorizations that different models do and are not shared, because in order for the average to be someplace, and for the weights to change from the pretrained model, they both of them had to change in the same direction. Because if a weight was somehow once increased and once decreased, it would more or less get back to the original point.
Yeah.
So there is some assumption that there is some regularization towards those kind of stuff.
Okay, yeah, very interesting.
It also might be related to some of the things that are good in this method. And I would say that I don't remember which paper, but I think in Alexander Rame's paper and maybe also in Gabriel Ilhauko's, they work a bit more on vision models, but they always make the distinctions between in domain and out of domain, and they show that weight averaging is often very, very good on out of domain distributions, better than for example ensembling.
Okay, yeah. No, thanks a lot for the intuition.
A question in the chat.
Yes, I think you're already reading it. Yes, so please.
Yeah. This might be slightly more general, but do you have? I'll read it to everyone. This might be slightly more general, but do you have some legacy model or method that you still find quite useful in your everyday work, like random forest or something like that? Okay, so I would say I would start from one thing that it a bit depends on what you call every day. But for example, we've been working on label sleuth. I didn't discuss it here, but it's a way that should be very convenient to label some data for yourself and have a classifier fast. The classification part is probably more useful for non-NLP people. And there, one of the things we found is that if we just use Word2Vec and SVM, because we don't have a lot of data, you reach very, very good results without large language models and those kind of stuff. So to have a lot of fast iterations, we can just use Word2Vec and SVM, and it works well. So I wouldn't say it's every day, but Word2Vec, people forget how good Word2Vec sometimes works with data. If you want something that is much quicker and dirtier, and you don't want to invest now something very big. Something else that is that I use that is older. Well, everyone uses BPE in some sense, which is quite old already. Probably there are many other things that I might remember with time. Okay, so I'll just summarize, and if you have more questions, it's a good time to think about them. So we said there are many base models out there, and a lot of the models that people share might be actually better than the pretrained model that they were based on before they shared the models. So we can go to Hugging Face and just find better fine-tuned models, or if it helps, you can ask our site and see whatever is currently leading or useful there. We can take several models and fuse them and get something that is even a bit better. And we can have iterations of doing those fine-tunings again and again and sharing. And as a community, we can incorporate our expertise and knowledge and data and computation and keep on improving models as we go. Yeah, so that was what we discussed today, and what I'm going towards is basically various ways in which we can accumulate our communal efforts in ways where different people could do different parts of the training and the architecture search and research, not even research, use. And by the different users of a lot of the community, could we have methods where the use would improve the overall model for everyone? A bit like a Wikipedia model. Could we have a Wikipedia structure to models where people that use it could, many of them maybe just be using it, but many of them would be able to contribute and slowly improve the model for everyone. And for that, we would keep on doing recycling and those kind of things, but also maybe we would need to improve other things, architectures or other aspects.
Yeah, thanks. Really great presentation, and we have also engaging audience somehow. There's already one question in the chat. Do you want me to read it out?
No, I see it.
Okay.
So the question is, do I see opportunities for distillation to fit in with fusion? And I think maybe distillation is one of the first things to be in it. I even have a small issue to myself in the ideas that if we have time, then we should check it. In a sense, fusion is one way of taking a model and incorporating the knowledge from it. And it's very useful in terms of compute. For example, this is the disadvantage of distillation, right? We need to reinvest compute in order to use the weights that are already there. But we might, as we saw, we can just take all of the models and use them at once. So maybe some kind of distillations could be used to gain more knowledge from different models. It is known that distillation is more efficient than training, or at many times. So maybe we can do some very efficient distillation or something like that to use models, and also about the architectural change. Maybe distillation could somehow be distilled from one model to another. I don't know, like there's always those places where people say something like, hey, T5 is not as good as GPT on Helm. And I'm like, could I somehow like get GPT into T5, because those are they were so much distillation, so much pre-training invested in them. Could we somehow collaborate between those efforts? So I think distillation is a great direction. I'm not sure if you also have. I'm not sure who's asking, but if you have, we can follow it offline if you think of something more specific that you want to do.
Yes. And I think if anybody has questions, they can also raise hand. I will unmute them and then you can ask questions. But in the meanwhile, we have this classic question from Munich NLP. What are your top 3 favorite papers currently that you have bookmarked and you're planning to read? So maybe we can ask this question while others are thinking possibly about other questions.
Yeah, well, probably it means something about the field that you assume that we
Yeah.
have 3 papers that we didn't read yet, but want to. So I'd say that for a long time I was in this problem, and I found out that it makes no sense, because like when I leave papers to read later, then they just stack up and become the 3 papers that I want to read, and they just replace which papers I'm not really going to read, but I would like to. So I dedicate some time to read in a more structured way in my time, and I assume that if I missed something, that I missed it and it's gone. Like if because I would always miss papers, and hopefully at some point I would get it back. So I don't think I have currently papers that are waiting for me. But there are various recent papers that are very interesting in those areas. There have been Joel Young's paper, I think. There's been a Dr. Soup paper not long ago, which is kind of like model soups, but with adapters. Colin Ruffles' group always have good papers. The field is, it became a field and not just like our 2 papers out there. So that's always nice.
Thanks. I see Maxim from in the chat. I think he's also one of the authors of Petals and Hive Mind, I guess.
Yeah.
And he's asking an interesting question. Thanks for insightful talk and for your work in this important direction. Perhaps I missed out this part of the presentation, but can we do some sort of collaborative pre-training this fashion with averaging with initial large pre-trained model when the initial large pre-trained model isn't available? In this case, you can't fine-tune it because you have no initial parameters. So can you improve an existing model by averaging fine-tuned versions, but you can't collaboratively pre-train something large from scratch? Yeah, this was rather.
Yeah.
large.
Okay, so I would say that first of all, one thing that we already know is that it's good to all of them start from the same random initialization, at least as far as we know. Yeah, you can always unmute yourself and have follow-up. But yeah, I think that the question is very clear. So the idea is something like that. First of all, you're right that this assumes that the starting point is already some large language model, which I think currently there are enough of them that we can assume that we can start from there. But there's branch train merge paper that kind of tries to do large language modeling by training on different domains and fusing them. And they did start from scratch. So they have larger chunks, and that the scenario is a bit different, but it still leaves me optimistic that it's possible to also start from scratch. I'm also not sure, I'm not sure we have to start from scratch, because there's so many models out there. As someone said, we can start from distillation, some other model, and then not start from scratch, right? Take GPT-3, distill it to your own architecture, and now go on and compute and continue from that. But to prove that exactly this method works for everyone probably requires proving, and I would guess that we also want something unsupervised. We would want some of the, or not unsupervised as itself, but just more data. So if we don't have enough data, we would probably want some of the contributors to create more data, but just training anything on unsupervised data. And that would go a bit more to the directions that I think you're also probably working on, but more on the directions of taking different people that would just fine-tune on whatever they want to. They would have a paracrawl or something of this sort to train on C4, whatever. And they would do kind of normal stuff and then fuse those just to get more data.
Yeah, thank you for the answer. It was really insightful. The reason why I asked it in the first place was that imagine that at the current point, we definitely have like many versions of BERT or like models at the million parameter scale, right? We have like also not more than one large language model available, like OPT or Llama and models like that. But imagine that the situation might change in the future. For instance, we observe that with larger scales come some additional capacities, some emergent properties of these models. And for some reason, we have no publicly available versions of those models. So you will essentially be interested in training something like that, like collaboratively.
Yeah,
but since you have no pretrained parameters of the scale, you have no, you have nothing to start from. So I'm just curious about how would it be possible to approach this topic. But I think, well, basically you've given an answer. Maybe you want to add something else?
I have given an answer, and I still stand behind it. But I think I have something else to add in this context. And it's also nice to meet you kind of in person. So one thing that I think is worth adding is works like there are starting to be a bit of works around. There's Lego from IBM, which I'm not sure how the paper is called, something around Lego, and there was like something with scaling BERT or something like that, that they start from a small model as an initialization of a large model. They somehow tile the weights and things like that. And then they show that this is a better initialization to kind of start running fast. So this, I think, is a very cool approach. And I was for a long time thinking about those kind of areas. Also, when I say change architecture together, one of the things that I want to try is something like that. Something like take whatever model, let's say you said BERT, so let's start from BERT, and could we now make from the largest BERT, could we now add some parameters in some ways, but keep the smaller BERT alive. And now some people would use the larger model, some people would keep on improving the smaller one, and then we can keep on enlarging it as much as we need, and having the emergent capabilities of larger models gradually. So the size could grow gradually. That's still an idea, though. The other things were papers.
Yeah. So basically, do you mean by this gradual growth the stage training paper? I think LNAI published something on it last year.
Yeah, right. LNAI also have something around those areas.
All right. Yeah, thank you. I think I should ask no further questions. Let somebody else ask them, but it was really interesting.
Please ask more questions. I think
Now someone in the chat.
it feels so good, yeah, that field experts discussing topics in our small Munich NLP community, which consists mainly of students. But yeah, great to see you. Thanks for joining. And yeah, let me ask the question from the chat. Awesome comments. Had some conversation recently about how distillation might help hurt catastrophic forgetting in context of online learning. Incremental fusion sounds like maybe a manual approach to online learning. Any thoughts on forgetting and how to guard against it? Let me also unmute NVB so he can ask follow-up questions.
Yep. So actually in the cold fusion, it was something that I was thinking of, maybe not as online learning, but at least as a continual learning or something like that. Because online learning kind of seems that you should forget the past. And what we did there as an initialization, as a initial trial, we trained on one, we fine-tuned on one data set, and then we didn't show it anymore during the next iterations. And we did it with several data sets. I don't remember how many. It's in the appendix of the original paper. And we've seen that not only that the results there do not decrease, they increase. So it's two things. One of them means that our experiment is not good enough, because obviously at some point we should forget things. And the reason that they increase is just because let's call them emerging capabilities for lack of another name, they just improve enough that they improve more than the things that we forget. But the interesting thing here is that we see that the decrease at least is very, very low. I mean, we didn't see even a decrease, but it still keeps the ability to do the same task without fine-tuning on it again. So what that might tell us is that this regularization thing might be very efficient for forgetting, despite having seeing tens of training on different data sets. We still didn't forget how to do it. So I think in this setting, it's very it has very positive. We can expect it to be a positive thing for the future.
I think there is no follow-up, but I asked him also to unmute just in case if he has follow-up question. Yeah, so potentially I see this your efforts and Max's efforts to be joining, also fusing, let's say, in the future, where people can hopefully distributively, collaboratively fine-tune these models and see. What are your thoughts on this? Maybe kind of Max's question initiated this, but do you have this in mind, or did you have this in mind?
Yeah, I think definitely it's
okay.
They have similar general goals in mind, and areas also, probably the solutions to similar things. I mean, I'm not sure what bothers him, but I would guess that certain similar things. For example, the comment about that somehow the largest models are currently not released. For me, it's not that surprising, because as we get to methods that are more and more centralized, so less people could do it, there's no bottleneck that forces some community effort, not on data sets, not on architectural sets, not on many other things. So when all of the bottlenecks could be done by a central body, then it makes sense for a central body to use it for their own goals and not share it with others, because they would not gain much from others, and the one that do not share becomes stronger. So those that share do not benefit from it, and those that don't share benefit from it. So slowly just like as a community thing, they become stronger. If we have technologies that are based on various ways of sharing, it could be sharing of information, data, compute, expertise. It could
Or
be all kinds
weights
of things.
in case of Llama, or just weights through
Yeah,
torrent.
yeah, it could be anything.
Yeah.
But just
Okay.
the fact that and even fame, right? Even if your fame was so nothing in the training, but when you have reasons to be in a community, then just the more community-based bodies succeed. And in those scenarios, I'm trying to find methods that are useful in community, like that are communal technologies that somehow create communities and not centralization.
Yeah, great
So
response.
I hope that
Thank you.
those technologies are good, but we need to find them.
Thank you very much. I think NVB is also now unmuted and he can ask follow-up questions. Do
Yeah,
you want
thank
to?
you.
Sure, no problem.
My name's Nick, by the way, just so I'm not quite so anonymous. And thanks for the talk. It's really fascinating. I just wanted to comment, I guess, after what you said about distillation. I mean, it sounds like extremely promising, especially these things about trying to have a community-oriented way to make progress. And one of the things I was thinking about in the background is that there's been some efforts to try to like one reason to do distillation is to just make running these networks more efficient, so you can put them on different applications, and there's even like different hardware architectures that might be able to run better if you can condense a network into a different format and things like that. So it's really unclear right now with the state of things if it's even possible to extract sort of the best parts of the network that are giving you a really good manifold that generalizes well, and then apply that elsewhere. It sounds like what you're doing is sort of saying that might be in fact possible in a really direct way, which would be super exciting if it were the case. But yeah, there's I guess a question here would be, is there sort of a like bigger picture, different architectures are going to create different manifolds, and how is it possible to fit those together in terms of like whatever generalized knowledge they've captured versus whatever memorization and overfitting that they've done on some specific task? Like, is there a way to tease that apart in some sort of like principled mathematical way, do you think? I know that's very far away from the sort of what you're trying to undertake with what you were just
I don't think it's
presenting.
far away in the motivations. I just think it's far away from what we really know right now. I think there is some hints that those things might be possible, and I think a lot of what you also mentioned is kind of related not only to distillation, but to pruning, and to there was pruning like ticket hypothesis before, but there's also pruning after, and all of those.
Definitely.
And I think that's also very relevant to the things that I'm thinking of, although I don't have currently, I'm not working on anything about that, but we can, if we also have some subsets of networks that are the essence of what each fine-tuning learned, then maybe instead of having a task vector, we can have a sparse task vector or something like a pruned task vector. And then, as you said, maybe this is the weighting would be easier. You can have more efficient models and those kind of stuff. So I think we have good reason to believe it's possible, but I don't think, I think nobody has already did it, and it would require some testing and finding how to do it well.
Thanks again for the talk.
Thanks for the question, Nick. So far, there are no more questions in the chat, but maybe Max has follow-up questions or yeah, let's see. We also check the chat. No. Yeah, let me just unmute.
Yeah, thanks again. So maybe I also missed one additional part of the presentation. I apologize. But so far, I think most of the results have been obtained on a class of models that are like primarily encoder only, like not relatively large. Well, by today's standards, models. Leshem, is that right, or maybe I've missed something? So I'm just curious about.
Mm-hmm. Yeah, you
Yeah, I'm just
didn't
curious.
miss, but we did have we have everything on T5, which is again not huge in today's standard, but it is not encoder only. Just to make it easy to follow, this is all Roberta based, but in appendices and papers, all depend on which paper exactly. So T5 is also showing the same thing. For example, in cold fusion, we saw it on T5 days and small, and one, not one, those kind of stuff.
Yeah, thanks for clarifying. Mainly the reason why I got interested in this is that, well, a lot of the community's attention these days seems to be focused on decoder-only models. Well, for obvious reasons. I'm just curious about whether you have like ran such experiments, or maybe some people who have ran experiments on this particular like topic of collaborative or iterative, collaborative and iterative fine-tuning, like with cold fusion, for instance, because. Well, if you have a way to reliably improve those models, it can give us some potentially very interesting further research directions.
Mm-hmm. Well, I would say that we didn't do on decoder only, but on encoder decoder. Just thinking about it, we never saw a decoder only and encoder decoder as inherently different in those areas. So I would be surprised to see that T5 works and GPT-2 doesn't. Not sure about huge models just because I didn't try them, but I have the assumption that they should. For example, Flan did on Palm. Palm is decoder only, right?
Yeah.
We see that multitask learning could help decoder only models. And in that sense, I would say that I wouldn't expect anything very interesting. Also, OPT, IML. So if multitask learning helps decoder only, then I don't have a reason to think right now that this is not just another way of doing multitask learning with some different details and probably differs at something, but my assumption is that whenever multitask learning should work, they should work as well.
Yeah, I mostly agree. I was just interested in like whether
in terms of specific trials, I only know on T5 and not on.
All right, I see. Thank you. I'm afraid I have no further questions at this point, but I'll probably follow up.
I think we can start slowly wrapping up. It's been almost 2 hours, and Leshem have been like machine gun. It was right 2 hours. Thanks once again for your time and presenting your work. I guess everybody who has questions can can reach out to him on Twitter or any email, his personal website. Yeah, I think we can call it a day. Thanks once again, and sorry once again for those at the beginning, some mishaps. We will try hard to solve them next time.
thank you for having me. And as
No
you
problem.
said, you're welcome to say
Follow
anything.
offline. Yes,
Exactly.
you can sync with him offline. Thank you. And yeah, see you hopefully next time.
Thanks for your time.